Recording. Welcome to the end of the semester. Got one class left on Mondays, huh? That's kind of weird. What? Gotta get your money's worth? Somebody's money. So the final exam review session. Yeah. All right, so what do you want to do? What do you want to cover? Anybody got any requests or something like that? How about we start out by talking about what's going to be on the exam? Good place to start. Good place to start. I'm going to put the thing up there. See, there's the title screen. Okay, now come up to camera. Motion sickness. Does it do it back? Get my table back. Something about having a clipboard makes me feel like an engineer. So, the old-fashioned clipboard too, the wooden one. I had a nice modern-looking aluminum one, and discovered that you might put that down on a steam pipe on a ship. Pick it up, and burn pretty little hands. So, go back to the old wooden one. Reminds me of like 1970 or something. All right, so final exam. What are we going to have on it? Well, the basic problems that we've covered since exam 2 have been fatigue based, right? There's often going to be, we always have our basic, the basic problems that we want to. We're probably going to cover. Going to be door handles, (3D) shaft, or just a 2D shaft. Pressure vessels. Or it could be like a pipe that's sort of like a door handle, that's the pressure vessel, that type of thing. We covered fatigue. We could endurance strength. With the modifying factors. The SN diagram for life estimate. We had stress concentration, fatigue stress concentration. With that notch sensitivity. We had the alternating and mid-range. I'm supposed to say mid-range. Fluctuating stress with safety factors. Soderberg, Goodman, etc. We could do a little bit of Miner's rule. Probably not Manson method. I think that's about it. Kind of things that we've done since exam 3. But they're all sort of like cumulative, right? There's sort of like a cumulative thing going on there. We could try to find some combination of doing these things. it's probably going to be 3 to 4 problems. Depends on how, I usually write the thing and then I simulate taking it and measure how long it takes me. And then I usually use a factor of about 2. Without like making, sometimes a little bit more of a generosity factor, not generosity, but just like a factor in there, something that's larger than 2 as a fact to kind of measure it. And then I go, that's not worth it. And then I take stuff out of it to try to reduce the thing down. So some years it's been 3 problems, sometimes it's been 4 problems. But sometimes I put extra credit on there too, just because I know that's get towards the end of the year. But the big thing is always the timing. And I don't mind giving some extra time on these. We aren't going to have the class coming barging in on us like we have in this room. That wasn't, we could have forecasted maybe that next time. So try to give a little extra time because I know the time is just the most, so it irritates you as much as it irritates me. I don't want people to run out of time. But then I have like a minimum amount that I want to measure. So those are sort of like the big ideas. And I say, sometimes I don't know if it's necessary or if it's useful for me to say this, but I really encourage you to do that way I just did before every exam and every course, right? Do it for yourself. Try to organize. Here's what do we learn? What do we do? And then as you go through, try to make sure that you cover all those things. Did we ever do this problem before? I can't remember. I'm losing track. I also have like this is a basic element. See, these are all the ones under review. I almost kind of want to do different problems besides these and leave these for you to do, just to test yourself. Here's another problem. I think I have actually used that before. I don't like this problem because I don't know what I was thinking back in the day. This is a log, non-log sheet. So it actually turns out to be a curve instead of a straight line. Here's also another problem. I think this is a challenging one. It's way too long to do as but it, if I could somehow shorten it down, I kind of like doing that type of problem where we have a pressure vessel combined with the door handle thing and loads in all 3 directions, and that to me is like, oh yeah, I like that. But maybe not exactly this one, but I kind of like those type of things. I'm giving it away to some extent. I haven't written it yet, so I'm not telling you exactly what I'm testing, but I tend to have something with a pressure vessel with additional stress on it is my tendency. That's way too small for anybody to see, so it's kind of a stupid slide. But maybe getting a Moore circle, drawing a Moore circle. Definitely want you to get the reactions in something. I want to see some statics to be able to get the correct reactions. It's important. And I measure it. And some combined fluctuating stress, like in this. So this is actually a pretty good problem, right here to look at. The fatigue stress concentration. And there's a 3D shaft problem. And this is good because it's relatively easy, right? It's not that mega complicated to each plane is kind of straightforward. And they didn't, leave out the thing where I have the missing pulley information. And then an SN diagram, going through the motion of using an SN diagram. And then maybe instead of using the equations, just use the graphic. That speeds things up a little bit. Not the rain flow, so that is not counted out. All right, so does anybody have any requests in terms of the kinds of things that we've done when we want to do? You have no idea how this would be along for the ride. Don't have an opinion. No.
Can you go back to the topics you were writing there?
Yeah, sure. We pick something out of the book. Chapter 6. That's basically main stuff that we're covering in here. And they have added some things in here since the last time I looked. potentially, maybe, not like that. Let's see. Have we done figure 656? In the figure shown, shaft A is made of this right here. It's got a force. I guess so. Let's do this one. So let's see. What do we got going on here? I'll write it down as you write it down. So this is 656. And let's see. We got ourselves. How long is that thing? Oh, it doesn't matter how long it is. And we got this symmetric little part right here running across, and these are only 1 inch each. Okay. 1 inch from the center, yeah, 1 inch from the center. And you're gonna force F up, you're gonna force F down. And this thing is 7/8 of an inch. And it's attached to the wall here, but it's got a little fillet of 1/8 of an inch. And anything else? Nope. All right, so it's made out of AISI 1020 hot rolled, and it's welded, fixed apart, opposite F, the theoretical stress concentration, oh, they already did it for us, of KTS equals 1.6. I already said it's 1/8, okay. They said that it's 2 foot long, but that does, I don't know if that matters. I don't think it matters. Because it looks like it's only going to be in torsion. All right, so that's going to make it just a little easier. And F varies. F min is equal to 150 pounds. F max is equal to 500 pounds. And we're just going to do part A. This is 1/8 inch. It's hard to see, isn't it? Is that better? Yeah, it's hard to see. That's 1/8. But we don't actually need to know it because they gave us the stress concentration. So we don't have to look it up. But if we did, what we would do is we'd use the D over D for that kind of stress concentration that would show up in here. Did I go by them already? Nope. So this is what we would use right here, maybe. And we would just pick the big one because this big D compared to that is like infinite. So that's the best information that we have. And then our R over D, that would be like 1/8, right? So 1/8, 0.125 divided by 7/8, which is 0.875. So you'd have like 0.14, so sort of something like right in there. So that's kind of like what we would probably choose, right, that we would have. And so ours would be a little bit less than 1.4, but they already gave it to us as 1.6, so I guess they got information from someplace else. But that's how I would have approached it if I had to. All right, so I wouldn't necessarily make you do this. I don't know, but I don't recall having done it before where I would like say, okay, well, we have this, so let's go ahead and look it up. A lot of times I'll give you that information, but I don't know, maybe that's worthwhile testing. It is really just, are you capable of navigating through this stuff? But what is this? This is 1020 steel. So we come up to 1020 steel and hot rolled, I think they said, and it's US units. So we want, really all we want is that 55 KSI is our ultimate strength. And so our SE prime is going to be 0.5 that, which is what, 27.5, is that right? And then we do all the KA, KBs things. It's hot and rolled, but I don't know what we would consider when it comes to the picking up the Marin factors in this. Just gonna have to make a good judgment call, I guess. Which is part of the thing that we're trying to do here, right? Is we're not only going through steps, but we're trying to use our critical thinking here. Oh, they have hot rolled. They do have hot rolled, so that's the one I would go with. And so A here would be 38 points, no, 11, because we're US units, and then negative 0.65. Trying to escape from that. So we go KA is going to be A SUT raised to the B. So 1155 raised to the negative 0.650. 55.65 negative, raise it 11 times. So 0.8131. I'm just going to multiply that by 55 right now. Okay. KB, before we do KB, we have to recognize that it is not a rotating piece, right? So first we need to have an equivalent diameter, and we look it up and we say, we take 0.37 times the diameter. .875. .3238, and then we plug it back into here. Remembering that if it was axial, we wouldn't do anything, but it's torsion. So, and it's less than, so it's in this range. So we go 0.879 and raise to that diameter to the negative 0.107. So 0.879, 0.875 raised to the negative 107. Whoop, I made a mistake, sorry. That should have been that 0.3238 raised to the 0.107. Make it negative, raise it 0.879 times. Ooh, all that work for 0.9917. Doesn't really do a whole lot. KC in the sunshine bag. Take a little look, get down in that. All right, so we go to here, we go, for torsion, we use 0.59. And we don't know anything else about the temperature. They didn't say anything about the reliability, and we pretty much don't use that KF for anything, so they're all equal to 1. So SE is 0.8131, 0.9917, and 0.59. 1, 1, 1, and times 27.5. And you might want to double check me on this because I have a feeling I overlooked something. 13.08 KSI is what I get for the endurance strength. And before we go any further, maybe I want to get the stress concentration. That might be something worth doing. They already gave it to us, but we want to modify it with our notch sensitivity. So I emphasize use the graph. Don't use the equation. Save yourself some time. So remember, this graph is for bending and axial, whereas this graph is for shear. And we had 55 ultimate, so that's close to the 60. And we had 1/8 of an inch, right? So that comes as a radius, so it's like right in here somewhere. So, damn, I think I'm going to pick 0.8. What do you think? It's just underneath the line of 60. Kind of runs right in there. I'll put my little weasel approximately in there. So the QS is approximately 0.8. So we have our KFS is equal to 1 plus QS times the KTS minus 1. So we're going to 1 plus 0.8 times, what did they say, 1.6, I think?
Yes.
So 0.6 times, I can do this in my head, can I? Probably, no? Yes, probably. 1.48. Sure. An extra zero in there. I think I have a lead emergency here. I brought some with me, that's all. Double check.
What was KT?
Say again?
What was KT?
KT was 1.6 because they gave it to us.
No, that was KTS.
The KTS, yes.
What was KT?
Oh, well, KT is they just add the S when it's a shear. So this is torsion. So they actually, I think in the problem, they did actually say KTS in the problem, in my recollection. What the hell's the good problem? Somewhere in there. Pages, stop. Yeah, so they went they went ahead and said it was KTS. So it was just the theoretical shear. I don't know why they make that designation. It just seems like a little. It made somebody happy. Maybe that's what it is. I don't mind making people happy. Okay, so that was getting just some low-hanging fruit things out of the way. Let's go back to what the stresses are going to be. This is going to be torsional, right? We know that. And we could do a free body diagram if we wanted to in different directions just to convince ourselves that there's not going to be any bending on this. Right? So it's a good, we can do it from observation, but if you're not sure, try it out and see. These are going to counteract each other. To go for the nominal stress in this, we might, take a little shortcut and say that the nominal torsional shear is going to be 16 times torque divided by pi d cubed. Right? I'm not even sure where you find that equation in examples and stuff, but we've seen for a circular cross section. It might save you a couple of seconds or whatever. You could just calculate J instead, go TR over J if you wanted to instead, but this is a shortcut for the thing. So the nominal min is going to be 16 times, oops, we're going to make sure we do this right. This is 150. Well, this is actually worth doing a free body diagram, because this is a good place to screw yourself up, right? So let's do an FBD. All right, I keep preaching it, so I should do it. All right. So here's going to be F, and here's F, right? And they're both going counterclockwise, so the reaction that's going to be right here onto the thing T, right? And the sum of the moments about the x-axis. And we're going to have F times this distance, which is 1 inch, right? But it has 2 of them, right? So you have to be kind of careful. You have to decide, was the torque, I mean, if you didn't do the FPD, you might go, okay, oh yeah, it's going to be 150 times 1 inch, right? But there's 2 of them. And you're going to go, oh wait, do I do it or don't do it? You know, you're not sure. Don't guess. Make an FPD. This is the whole purpose of the thing, is to like solve those, like, you know, little tiny things that could jump out and grab you. But it's a big thing because it's going to be twice that, which you might accidentally think. So it's going to be, you know, F times, I don't know, I'll call that distance D, plus F times D, right? Minus T equals 0. So what you're going to end up is the torque is just going to be 2 times 150 times 1, or 300 inch-pounds. And the same thing is true for this one, right? So it's going to be 1,000. All right, so I wish I had more room here, making a mess. But we're going to go that T min is 300 inch-pounds. T max is 1,000 inch-pounds. And yes, we could have done that in our heads, but we have that danger that we're going to mess the thing up. So, I mean, truthfully, wouldn't take off points if you got it without doing the FPD. But you get it wrong without doing the FPD, I got to take off points because it's, you know, these are critical things to being an engineer. Don't get the thing wrong because you took a shortcut. 0.875 here. And so, cubed. We might want to take a shortcut here too, and as we're going max 16 1,000 pi 0.875 cubed, and say 16 times 300 divided by pi 0.8753 raised to it divided, I get 2.2, I divided by 1,000 as well, KSI. And now I'm just going to divide this by 300 and then multiply it by 1,000. Boom. So I saved myself a little bit of time right there, right? There's some time savings by not plugging all of that into the calculator again. These little things can add up. And now, maybe I'll go ahead and, it doesn't matter when I multiply this by that. So I could just go ahead and say that my alternating, I guess I'll say, I can't decide which way to go first. We're going to go nominal alternating or nominal, but anyway, we'll go, I won't write out the symbols for it. It's just going to be 7.602 minus 2.281 over 2, right? And let's 7.602 2.281 minus divided by 2, 2.661 KSI. And so I'm coming up onto something that it's, to me, is going to be an interesting thing. Trying to think of the way it says right here. It would be a revealing thing about whether you understand what's going on. All right, so, oh, I made it messed up, sorry. My bad. These are tau. right? They're still tau. They shouldn't be sigma. And now I'm gonna, I'm leading myself down a stray. The tau amplitude should be KFS tau nominal, or 1.480, 2.661. So 1.48 times 3.938. Same thing for the tau mid-range. .313 KSI. Here's the telling thing. Should I turn these into von Mises? What do you think? You know, Admiral Akbar. You get Star Wars. No, I guess it was Return of the Jedi, right? Yeah. It's a truck. It is. It's a truck. Should we turn into von Mises? I'm implying no, right? By me asking. And you're afraid of my check. Why no? What's that? No need. It's true. It's true. Right? What did we do? What did we do right there? What was that value for? Yeah. So we have already converted our endurance strength into a torsion endurance strength. Therefore, we don't need to turn it into von Mises because we're comparing apples to apples. Von Mises is, remember the whole von Mises conversion thing for shear, pure shear, is 0.577. Right? That 0.59 is really close to that for a reason. Those two things, you use one or the other to do the conversion, but you wouldn't use both. Right? So if we left that 0.59 out, yeah, then convert it into von Mises. And you're nearly at the same place.
If we have X, we would have to do.
Yes, if it was combined with something else, you treat that KC as one, and then you do the von Mises thing to combine it, right? Does that make sense? That's like the spirit of the thing. That's why I said that's a good one to try to measure. You see what's going. Do you really see what's going on? That apples to apples wasn't just a fun little fruit reference, right? It's the underlying thing, principle as we're trying to approach stuff. All right, so this is, now we want to use Goodman, right? Well, here's actually a dilemma. Ooh, that's a good dilemma. All right, now we got to, I see why this was at the end of the chapter. Because this is like something I hadn't actually, maybe I made a vague reference to it. Remember what Goodman is. Let's take a look at Goodman. 1 over sigma A over SE plus sigma M over SUT. What did I just say about sigma, about SE, right? That's already for shear. But what do I do about ultimate? Well, if we had paid close attention, and I don't think I would ever ask this question here. I know it's in here near, but I don't know, I'm not as familiar with it as I should maybe. The surface fatigue strength roadmap There's a reference to ultimate shear strength somewhere. And my recollection is it's not exactly that 0.57. So indulge me here for a second as I try to look that up. But once again, this would be a little on the evil side, so I wouldn't do it. Maybe a younger man. Maybe I would as a younger man. But we have surface fatigue strength. I know about that. Do we have ultimate fatigue strength? On the ultimate shear strength. Well, you know, they make an index for a reason. It's probably in here. Oh, there you go, right there. Boom. It's in the book. It's fair game for many professors. I don't like playing that game, but there it is right there. You're going to need ultimate fatigue strength in order to use Goodman here. And this turns out to be 0.67, right? And that's just application to a pure shear case. I wonder if we did have to do that, if we did have to look it up. Could we look up ultimate shear strength? Or shear strength ultimate? Ultimate strength, ultimate tensile strength. Nope. What about shear? Yeah, I tell you what, a lot of times I'll judge a book by how well it'll do me right when it comes to shear, when it comes to the index. I don't like books that don't have an no. There, bad, naughty. Okay, but anyway, that's the thing that we would do for this problem, and probably why it was in the latter part of the chapter is it's going to, they usually, I mean, they correspond to the sections a little bit in terms of the order of problems, but as you get later and later in the chapter, they tend to, I mean, in the problem section. So what I would say here instead, Goodman, should be 1 over tau A over SE, that's been adjusted, plus tau M over SSU. So the SSU, according to this, is 0.67 times 55. Does anybody have a book with them by any chance? See, can you see if this problem is actually in the back? Only if you don't know. If the answer is, I mean, there's a chance we got it wrong, so I don't know. But I think that's the trick that kind of like got revealed as I was going through. I'm like, oh, I see what you're doing, you sneaky dog. 3.938 is what we got for the alternating. And that gets divided by 13.08. And then our mid-range was 7.313. And that's 36.85. So there you go. They're right there in my calculator. Just doing that there. And then flip that around and go 13.08 and divide. Add them. Take the inverse. Ooh, almost exactly 2.0. Is it? Oh, well, that's probably good for me, because then I don't look like a chump for getting around in. You know, if my ego was the important part, right, I can survive. I can survive another day. Well, when I go back to the safety of my office, I'll find out if I got it right or not. I would encourage you to pick a random problem that you have an answer to.
Where was the equations for the adjusted ultimate?
That was on page 337. It was just to the end. It was right before the example 612. where they were saying, notice some of they're having the same, right here is a written out, same discussion as I was trying to coax out of you, right? That 0.59, like you want to do either or, you don't want to do both things, right? So if you're going to, if you wanted to use like Soderberg, you'd want to use the shear yield instead of using the regular yield, right? But here's for most applications, it's somewhere between 65 and 80, lacking specificness, justifying a higher value, use a conservative estimate of this. They don't really go into much more detail, but this is a good example in terms of trying to think your way through a problem, not necessarily for the exam, because I'm not going to try to trick you, not in that sense, but it does push you a little bit to look beyond the cookbook nature of a lot of problems. All right, what would you like to do next? Suggestions? Say it again? Okay. They don't have a whole lot of examples, a whole lot of problems in the book doing that, unfortunately. I can attempt to try to think. There's a number of things in. So I could try to do, yeah, 660. Let's see, that looks like a miner's rule here. Right, so a rotating specimen with an endurance limit. So they already gave us, this is probably 660. The endurance limit of 50 KSI. Ultimate strength of 140 KSI. So 20% of the time, it's going to go, so this is like event one, you could say, 20% of, okay, so this is actually a little bit more like almost like that raindrop thing. It's the equivalent of the raindrop thing, of the mentality there. It's the damage fraction rule. So it is miner's rule, but it's a damage fraction concept. So I'll show you what I mean by that in a minute. But 20% of the time, it goes between, is cycled, okay, cycled 20% of the time at 95 KSI, 50% of the time at 80 KSI, and 30% at 65 KSI. All right, so, damn, this is going to be, I don't know if that means it's on, off, the way that the words matter here. This is not a good example for the example, but it is a good example to stretch your brain and understand the topic more. But it's the wording of this and the word problem, cycle. I think it means it's on, off, not going completely reversed, right? So it's 20% of the time, it's going to be at 95 KSI. So event 2 is 50%, is going to be at 80 KSI. And 30% of the time, it's going to be 65 KSI. And I'm going to estimate the number of cycles to failure, right? And so like the cycle has to be kind of defined, like what constitutes a cycle. I guess maybe you're just going to say, yeah, I guess, yeah, okay, that makes sense. All right, so, yeah, so it's portions of the thing. It's the damage fraction rule concept. And they also said let F be equal to 0.8. So there's a couple of things here. All right. First off, in this problem, in this concept, I'll write out that the idea here is all of the damage fractions have to equal 1. So what you could say here is number of cycles I over Ni, right, is equal to 1. And so what that turns into is like if you have 0.25 of let's say that we're going to replace Ni with just little n, right? All of them are the same cycle, but they just have a percentage of cycle. So you would just say little n over Ni plus little point, let's say N1, sorry, 0.5 little n over N2 plus 0.3 over N3 equals 1. So what you could do then is just bring the n to the outside, and that's the thing we're going to solve for the number of cycles, right? Just at 0.2 over N1 plus 0.5 over N2 plus 0.3 over N3. Does that make sense? Because I just said it's cycled, so it's got to be number of cycles for each of those things. They're all sort of equivalent to each other. So what we have to find is this N1, N2, and N3 for each of these scenarios, for the 95, 85, and 65. So for case 1, we know that the mid-range and this are going to be equal to sigma max plus sigma min over 2, which is just going to be sigma max plus 0 over 2, right? That's the assumption I have to make, that it's not a completely reversed thing. They were trying to mess with us a little bit. So in this one, it's going to be 95 divided by 2. Can you do that? Is that 47.5? And then, therefore, we want to find the equivalent completely reversed thing. And, I'm trying to think now. That's a little tough because that's less than the endurance strength.
Since it's rotating, so if it's rotating, wouldn't it be fully reversed?
Let me think. Does it say that? A rotating beam specimen. You're right. Okay, that makes our job easier. We don't have to do this stuff right here then. So that means that this is sigma A for all of them. I was thinking that they were trying to do that with the you know, See, I'm trying to wonder why they gave us the ultimate strength then, in terms of the way that they wrote that. Because I was thinking that we're going to need to do this right here, right? Oh, I know why. Because we needed to get the life. I don't know. Okay. Because what we needed to do was we needed to find A and B, and so that's F SUT over SE, right? Squared? Don't go by memory. If you can, by the way, you know, it might be useful to just make yourself familiar with this part of the book right there, right? And 19, because you could just jump to some of these things, right? So like right in there, so like right there. And I did it wrong right there, yeah. See? Don't rely on your memory. But know where the stuff is in the book. Put the tabs in there to save yourself some time. So it kind of saves a little bit of time to do this over to the side where you were at 0.8 times your 140. Should be able to do that in my head, but I'm not. 112. So you got 112 squared over 50. There you go. And so 250.9. And this is a negative 1/3. I'm looking at it now. Log base 10 of F SUT over SE. So we're going to have 112 over 50. Oh, yeah. And take log of it. Divided by 3. Negative 0.1167. So for N1 is going to be simple. Remember, that's going to be sigma over A raised to 1 over B. So we'll take 95 over 50. Whoop, no, sorry, 250.9 raised to the 1 over the negative 0.1167. And I take 1 over that. Okay, so that's not a lot. 4.099 E3. It's pretty up there. And 2 is going to be 80 over 250.9 raised to 1 over negative 0.1167. So we'll go 80, 250.9, flip them, and we gotta invert them, raise them. So it's a 1.786. Seems like this should have been E4. Okay, yeah, it is a bit bigger. And that comes out to 65, 250.9, and to the 1 over negative 1167. So 65, 250.9 divided 0.1167 inverted raise 1.063 E5. So coming back up to this thing up here. 0.099E3 plus 0.3, 1 point, no, not 0.3, 0.5. We keep them straight here. 0.5, 1.786E4 plus 0.3, 1.063E5 equals 1. So we're going to take all that and then invert it, take the inverse of the thing when we get over to it. So we have 0.3, and my answer is, and you can almost think of this as sort of being sort of like a weighted average. So that's 12,561 cycles. So for an answer, I say 13,000 or 12,000. I don't care. Round up, round down, doesn't matter to me. Just don't make it seem like you know exactly what the result is going to be. Does that kind of make sense? I don't really do this as problems in class, but it's worth recognizing that is the minor rule. Minor's rule is the damage fraction rule. And so much easier to do than Manson. Manson requires like these multiple steps, but it does illustrate that minors is deceptively easy, right? It's just a quick way out. Any chance that wasn't in the back of it? You didn't look at it, not. So my ego stays intact? Okay, good, thanks. So I need that. Any way I could get, I'll just, I don't know. We do some kind of design problem. We'll work our way backwards for some kind of design thing. Maybe we want to make a door handle. We want to design a door handle. Are we I don't know. Seems pretty, yeah, we can do it. I believe in us. What's an inventive problem? Danger. US units or metric? Metric. Oh, invention. Okay, so what is our new thing going to be for? Any applications? Maybe we're going to have something that goes out and up and over and out. Right here. The sky is going to look like this right here. It's going to come upwards. It's going to go over to the side. And it's going to be like that right there. It looks terrible. Sorry. Trying to make it look more like a real thing. Right? This is the X direction right there. This is Y. This is Z. How far is that thing going to go? 1 meter?
Yeah.
How far up? Half meter. Right? We're going to measure them right over here. What about this guy? Okay. A little symmetry. Okay. And him. How much you say?
1.
Another 1 meter? Okay, wow. Yeah, this thing's huge. Right. And then we're going to be loading it up. We're going to go upwards, downwards. How many newtons?
75.
75? All right, sounds good. Want to go left or right? 200? Whoa, okay. And then what, we're going to go in or out? That's in. This is out. In? Anybody? 50, okay. All right. We've invented ourselves a problem, and now we want to find out what the diameter has to be right here. Are we going to have stress concentration? Always. All right, what kind of stress concentration, what kind of thing is going to be right there? Let's say the thing keeps on going maybe a little bit, and they just made a, let's say they gave us one of these. But we're going to have to guesstimate this because we don't know, right? We don't know the diameter of the thing yet. So we're on the design side. So we want to design this thing for failure. Let's say we want to design for failure. Yeah, we're just going to say, we want it to fail. Like maybe even at a particular thing. So we take and say, maybe we work backwards and say, I want to make this part because I want to sell more of them. So we'll be able to choose what our choose all of these other dimensions. What we're really going to be designing for is kind of this D right here. When everything's said and done, because we'll be able to pick what the other one is going to be, the big D, and we'll also be able to pick the fillet radius. So, like looking into here, I'm going to go to the middle of the road. Let me pick 1.8, right? Same, but we should pick probably the same kind of thing, like in the 1.5, and looking back up on this ratio, they had the 1.5 here, so maybe right in there. So that's probably going to be the middle of the road of like 1.6. Anybody paying attention? It's 1.8, 1.6, and kind of the same idea, but here that's actually 1.3 right there. So I'm going to say this is going to be like 1.3. We're really just making things up now, right? So the axial was 1. Did I say 1.8? I think it is. And the bending was KT, I think it's 1.6, and the torsional was K, that's a KTS, and this is 1.3, right? When we get to that, I think I'm able to do this, but I don't know. And we're going to do it for fatigue, right? So we got to pick out a material at some point. So, and we don't know anything about the, we don't know a whole lot. We can go machined, and we can pick out a good old, well, I don't know the conversion on the top of my head to A36, but we can just stick with like 1020 steel, because that's probably like right around in the A36 range. Probably actually stronger than A36. I'm thinking. So if we're going to go, let's go 1020 cold drawn steel. So we have an ultimate strength of 470. Megapascals. So without going too crazy, because we don't know the size, the factor, and we could go for the machine thing. So say it's machined. So SE prime is going to be 0.5 and 470. Can't do that in my head. That's sad. But as Clint Eastwood tells you, a man's got to know his limitations. I don't remember what movie. I think it was a Dirty Harry movie. Man's got to know his limitations. Except they said it cooler than that. 3.04 is that, and we go 470 and raise it to the negative 0.217. So 470, 0.217, but make it negative and raise it to it. That did not work. Oh, I see, I did. I hit the wrong button. Right there. Okay, cool. And then 3.04 times. So that almost comes out to exactly 0.8, by the way. 0.7999. And we'll just keep KB is equal to 1 and all the others. So our SE is really just going to be 0.7999, 235, or 188 megapascals. Okay, great. And we'll use Goodman for the thing. We need to get, and these loads, let's say they're, let's say they're on off. Like this happens and then it turns off. Right? So that means that our mid-range is going to equal our alternating. But we're going to have to take 1/2 of the loading. So one of our first tasks, we know the axial is going to be this load right here. That force is going to be completely on and off. So that's already, so the alternating axial is 25 and the mid-range axial is 25 newtons. But we need to get the torsion and the bending moment. So we have to do FBDs on this. We better. So I get started. The only thing to do is to do it, right? As tedious and annoying as it might be, it is just the way it is. So we're going to look at this thing and yeah. Sometimes I like to put the little shoulder in there. This is the little, we would see that shoulder right here. And we're going to see the 75. And we're going to see the 50. This distance is 1 meter. This distance is 1 meter. And this was our point 0.5, right? Yeah. So we want to draw the reactions. It's really important to me that you draw the reactions in kind of the right place. Whoop. Maybe put them in the right direction though. I know that they won't really, these are really kind of rudimentary. We don't, we could just say, oh, we know that one's 75, but do it anyway. Put them in there. Now here's where we got to ask ourselves, all right, this guy counterclockwise, this guy counterclockwise. This must be, so this is going to be M about the Z. It's going to be the reaction about the Z. So summation of moments about the Z is equal to 0. Please write that. Don't say equals and then start doing anything. I know there's professors that do that. I don't wish they wouldn't, but then I can't control other people. My wife says that. She tells me that all the time. And by the way, I just mentioned my wife. There you go. Seems a little. You seem a little obsessed with her, Doctor. Is this a healthy relationship? I don't know. I shouldn't question it. She did say that she hates other people. Just so it says it. And this is being recorded, so this for posterity here. Lori Diane Dapperdale said she doesn't like other people. So now it's recorded here. She is one of the nicest people we've met. Secretly. So I got 175. What do you think? Sound right? Newton meters. All right, let's see. I'm going to keep this thing on here. So I'm going to be able to look at it and draw it. No, it's going to be too small up on the screen if I do that. I'm going to look down upon it. And if I look down, it'll be like, you're going to see the top of that shoulder over there. Right? I think so. And let's see that force at 200. And let's also see this 50 again. And this will be 1 meter. And this will be 1 meter. Not to scale. And this one's going to be 0.5 again, right here, right? Because it was that one right there. So let's see, here's our reaction. I didn't draw my axes. This is going to be the XZ looking down on this thing. Here, so this is the reaction in the Z. Of course, the reaction in the X is still there. And in terms of a moment, did we do the thing? Look at that. We were able to make it. They're both in agreement again. All right, all right. I like it when they go disagreement. It's a trap. Well, more Admiral Akbar action for you there. But that's not RY, that's MY. I had started writing MRY in there, right, to separate the thing out. Should be consistent. Huh? Yeah. I'll put it in there now. I guess I could have stuck him in there. And summation of moments about the y-axis. And 200 times 2 plus 50 times 0.5 minus MRY equals 0. MRY should be able to do this in my head. That should be 425, right? Shouldn't trust my head. I know, I don't. Last FBD in our design project here. Okay, so we're going to be looking down the length of this thing in the YZ plane. And it's going to go up in the Y, over to the Z, and then into our face. So up, then it's going to bend around, and then it's going to come right at us. And then we're going to have 75 coming up. And we're going to have 200 going that way. Finally, we've got one that's going to like argue with it. So our reactions are going to be arrow down that way, this way. So this is going to be the RY. Here's our RZ. And then moment, well, let's take a look here. This dimension right here is 0.5, isn't it? Let me double check. That's that guy right here. And then this dimension is 0.5. You people in your symmetry, but they're arguing with each other, right? So this one's going counterclockwise, this one's going clockwise, but they got the same moment arm, so if this one's gonna win, so the reaction better be counterclockwise. You see the logic? And this one's gonna be the torque. So I'm going to go a negative 200 times 0.5 in a in a positive 75 times 0.5, and then a positive MRX equals 0. I know. So that should be 100 minus 37.5, right? Don't trust yourself. 200 times 0.5. Did I just really do that? Yep, good. 75 times 0.5. Boom. Subtract that. Yeah, 62.5. That's equal to the torque. So now we want to get, this is both going to be the alternating and the mid-range. No, that's not true. We have the one half of that will be alternating mid-range. This is equal to the max. We also want the max moment. So that's going to be bending about both the y and the z, which is going to be 175 squared and 425 squared. So we will have .6 Newton meters. So let's go alternating and mid-range force is going to be 50 divided by 2, because that's the max. So 25 newtons. The alternating and the mid-range is going to be our 459.6. Everybody knows why, right? I just did a shortcut. There's max plus min divided by 2, or max minus min divided by 2, either way. Those are going to be, so we get 229.8 Newton meters. And then the alternating and the mid-range is going to be, we have that 62.5 divided by, oh, why did I do that? Because your brain just shut off for a minute. Keep thinking, all right. 62.5 divided by 2, 31.25. Should be able to do that in your head. Didn't. All right. So let's see. Anything else we see? It doesn't make a lot of sense in our design philosophy to really do the notch sensitivity to these. We know the notch sensitivity is like in the, it could be like 0.8 range. It really depends on what we choose. So this is design, so maybe we want to come back and look at this later. We do want to kind of maybe aim for a life, right, that we want to have for this. So I don't know. Maybe we want, let's just aim for 1 million. So then it's SE. Then we're going to aim for SE. We're going to aim for 1 million. So that's where we're going to go. All right. So now we have to go. Let's see, where do we go in the book? There is a nice little section for us where, do they do the design thing or do they leave it to chapter 7? But even though chapter 7 is about the, what we're really going to do is use these backwards, right? Alternating in mid-range, but we're going to use them backwards with a circular cross section. And I don't see this chapter 6 have anything along those lines. No, they don't. Okay. Okay. So good chapter 7. Design something to think. And chapter 7 is a weird little thing, but we can do that. We'll follow the 11th edition's thing. Where we do go A and B. We know all of these things now. Well, actually, we have a little bit of a dilemma. We don't have any axial. They left it out. But we can assume. Yes, sir.
Can you go back to the calculation of the moment max?
Which one?
The calculation of the max moment.
Yes, sir. Sorry. I didn't mean to go too fast.
We look at this weekly. Oh, never mind. Okay, never mind.
Okay.
No. I still need the.
Oh, okay. Okay. I'm sorry.
I just was confused about a certain calculation, but I noticed it.
Oh, good. Yeah, they didn't do the axial in the shaft section, so I gotta try to think this thing through. I guess, even though that's a compressive axial, I have to make a decision here. It's a compressive axial, and the bending is both compression and tension. So the bending does both compression and tension. So on the tension side, it makes the tension less. But on the compression side, it makes the compression more. So I think we're still going to add the two things together for the worst case on the thing. But I got to wonder, if that might just be a conservative thing to do. I'm trying to decide. I think it's still going to be appropriate to add them together. So even though, but, oh, that makes it more difficult. Yeah, we're going to have to ignore the axial. In order to use these equations, my conclusion is, all right, so they did algebra for us, obviously, right in here, right? They went from these things, which are, well, they're showing them right in there. But yeah, I think that's going to have to be our thing. Now, the axial is going to be small. If I were to maybe to do this without, not in a non-test situation, I would probably make a spreadsheet out of it because, and then work backwards instead of doing the equation. I would do the goal-seek thing. But let me write down, in our pursuit of a more complicated problem, that A is the square root of 4kf MA squared. And these are going to be equal to each other, right? Because everything else was equal to each other. Right? Because we had, so we're going to ignore, unfortunately. But that 50, remember that 50 newtons did contribute to the bending, so we're not exactly ignoring it totally, but we're just ignoring axial stress because it doesn't come out to be in the same order of magnitude as the others, right? So we know that B is also going to equal this, right? So if you look at that equation right here, you can see that, it's just these values, the A and the M is equal to each other in both of those. So we have 4 times, and our KF for bending was 1.6. We're ignoring the notch sensitivity, and the moment was the 229.8 And then both of those things get squared, and 3 times the KF, which was the KFS, which is 1.3, and the torsion is 31, so it doesn't really do quite nearly as much. But it does have a 3 in there, so either of those things is going to be equal to 229.8 times 1.6 and square them and multiply them by 4, and then take 31.25, multiply by 1.3 and square it, and then multiply that by 3, and then add them, and then take the square root. And so this is 73.87. And I think it will be a Newton meter. And then for Goodman, we're going to write out this equation right here. We'll do the SE and the SUT so you can see. And we're going to make a safety factor equal to 1 because we want the thing to fail exactly at that 1 million thing. So D is equal to 16N over pi A over SE plus B over SUT 1/3. Now I'll do it down here. 16, 1, because that's we want it to fail. A 73.87. SE, we came up with 188 plus 73.87. Well, we got to be a little careful here. E6. And this should be ultimate strength is 470. 470 E6. Yeah, I forgot. That'll get us into meters. Because this is a Newton meter thing right here, right? Because this was a Newton meter, and this was a Newton meter. The rest is dimensionless. We squared it to the square root. So this is a Newton meter, sort of like equivalent. Although it's not exactly any particular value because that 16 and pi are things that are in there. What's the matter?
I got 738.
I wouldn't doubt it, and you're right. Thank you. Appreciate that, especially since we're about to plug all those numbers in there, right? You're right, because I just didn't, I looked too quickly. I had the E2 right in there. I get a little fatigued. I get tired of my own voice. Oh, and everyone goes, oh, we know. We know what that's like. We can relate. Times pi divided. All right. Now I'm going to raise it to the 1/3. I hope I get something interesting. Is this interesting? So we're getting near 30 millimeters. So in terms of design, I have some control over my stress concentration, right? So I can tweak that and pick the 30 millimeter and then just change what my radii are and my big D to like hone this down. So I'm going to say D is equal to 30 millimeters preliminary. And then maybe I'll go back and look through when I picked out these guys, and then I also might want to go and use, as I'm trying to do this, to try to aim with that notch sensitivity as well, right? Work backwards, because I really just picked these out of thin air, right? In terms of my design, but that's like a design mentality. But now we have a problem that we could start in the other direction and say predict a life of this or whatever you want to do. So you've helped me create a new problem. This will be on the final exam next year, and this will be recorded, so anyone that actually listens to this whole thing will have a leg up on everyone else. I think that's fair. Make like a little Easter egg thing, that someone would actually go to the trouble of watching this video all the way through to the hour and 36-minute mark. Yeah, maybe that's fair. We design next year's final exam problem. All right, what next? I mean, I don't want to put pressure on you. Some pressure. What pressure vessel thing? We'll do pressure vessel probe. Oh, pressure vessel. Maybe a little maximum shear stress one. I don't know. There's a good one for maximum shear stress. Or a more complicated von Mises, right? So you can't use just your own regular von Mises. Let's go to this other problem. I don't know. Let's go to an existing problem. We're way too much imagineering. This guy right here, look at him. So I'll write all this stuff down. And this has too much stuff going on to it to be an example. Right? What if you could do this? You could do the other. And I don't know. Do we want to go to the max for this thing, or just to a particular location? Let's go to a particular location. Because we've been doing the max thing, right, where we find the max. It asks for it at K. Let's see, which one would be better? I don't think it matters. Yeah, let's do a K. And that's what, 14 kilonewtons, and downwards of 10 kilonewtons. My band's playing at Groton tomorrow night. Circle of Willis. I know, it's a terrible name. The blood vessel in your brain. Circle of Willis. Looks like a little dude. That's what I'd like to see. Circle of Willis. Yes, I came up with it, but I just threw it out there. Circle of Willis. See, it's an actual thing. See, this looks like a little dude. I thought that was kind of cool. That's this little brain, this little blood vessel, and it does a couple things. It acts sort of like this shock absorber for your blood in your brain. Because why did it just? It's like a turnabout. It's like like one of those traffic circles in your brain. And if you go to like Etsy, they sell little bracelets and stuff. It's not that obscure of a thing. But also, did you ever watch the TV show Different Strokes? Of course you did, because that was like 1981. But there's a little dude named Arnold, right? And he'd be like his older brother, and the little kid, his little tag phrase is, "What you talking about, Willis?" That was his thing, right? What you talking about, Willis? So Willis just has this funny kind of connotation to it. Yeah. So anyway, I thought that was important. Planet 40 Thieves, and you will not get any extra credit if you show. Just so I wouldn't do that. But I just figured I'd mention it. Why? I don't know. It's on my mind. The classic problem with being in a band is that you want to play places where people are already going to be, but the club owners want a band that brings people with them. It's like two completely opposed things. So in this, we want to find the three principal stresses and the von Mises stress. Sure, don't neglect transverse shear. So we got a lot of stuff going on. All right. Put that in your pipe and smoke it, all right? So because that looks like a pipe. Old Glory. Get yourself a pipe. Alternative tobacco smoking devices. All right, I'm gonna do the all of this stuff here. Pi over 4 OD minus ID squared. Let's just pretend we did all this, right? Because I know that I have these values already. And I'm getting fatigued. We've already established that, right? Yeah, looking in my side, we all also did the thing with the thickness, right? So this is sort of like some things that were kind of given to us. 1.414 E minus 3 meters squared. 1.436 E minus 6 meters fourth. We could actually just narrate this, couldn't we? We want to write all this shit down. Maybe. I don't know. What's the point? Yeah, sure. You better make this into an animation. Nah, let's go through. Don't be lazy. Don't be lazy. I feel like you're being lazy though. Let's see, what else do we want to do? Oh yeah, the thickness of the thing was 95 minus 85 divided by 2, so it's 5 millimeters. So our T over R, and we might want to get our R somewhere, right? Oh, that's just sort of 5 over 95 divided by 2. So it's thin. It's close enough to being thin, don't you think? Yeah, close enough to being thin. So I did it both ways actually in here. So in here, let's get rid of that. Get rid of that. I know that I have a video of me doing this before, so. Let's just take a look at it then. All right, so the bending, so the axial is the same everywhere, right? And that's not going to be the same. That's going to be 7 kilonewtons in that area up above. That's going to be compression. And I didn't put in what it was. I don't know if those are megapascals or not. Yeah, I think no, those must be just pascals, right? So I don't think that bending is going to matter at all. And I wrote bending there when it should have been axial. That's why I keep saying bending. But you agree that's probably right, because this is 7,000, but it's divided by e to the minus 3. So who cares? You see it H. So I already did this up here for you. I don't think there's anything in looking at this right here, right? Right here is about this is about the x-axis. Yeah, these actually do, you'd have to, you would want to do this FBD on here. Because, you know, this one wants to go clockwise.
I think the axial should be.
You think this should be?
Yeah, you divide by.
Oh, yeah, you're right. Yeah, it is. Okay, sorry. Yeah, so she. So maybe it will matter a little tiny bit. Yeah. And then notice that I did the thick and the thin here. I guess I decided to go with the thick for this because I wrote down here just for your FYI. But take a look at the hoop. Yeah. Yeah. Oh, am I doing the inside? Yeah, I think I'm doing the, yeah, okay, so I'm fine there. Got 85 versus 80.28. So the thin is actually more. Yeah, similarly right here. The torque is pretty substantial compared to not to this guy. This guy right here, this bending at K, he really does a whole lot. Yeah, and then here's the transverse. So you got to make the decision how these guys add to each other. Let me bring this back over here. Oh, there it is. We did it right there. Okay. So the axial is compression at both the H and the K. The bending and the longitudinal, right? All of those things are in the Z direction of this guy, right? Which is going to show up. Yeah, both of these are Z. That's a Z right there, and that's a Z. And in the H direction, or no, in the X direction for H and Y direction for K, we have the hoop stress, right? Or make sure we remember the hoop is by itself. It's the only one that's going to be not kind of like along the long axis. It's the one that's trying to make it a hoop. It's trying to expand the thing. It's trying to make the thing bigger, but you don't combine anything with the hoop. And here's one where it would be good to look back and see in the transverse in the H at H right here is going to be due to the 14, right? Because like if we're looking down the length of this thing, the 14's coming down that way. And here's the top right here is where that H is going to be, right? As opposed to over here where the K is, that's going to be the 10 because it's coming down that way, and therefore it causes shear right here. But then you got to notice that the torsion on this is pretty much due to the 14 and it's going to come around that direction, right? So it's going to agree at H, right? Because that's going to have, both of them are going to be going towards the negative X direction at H. But at K, the transverse is down while the torsion is up. So they'll disagree with each other. Or they should. Okay, so this guy should be a negative, but I do put him right here. I got that right? On here? It doesn't matter which one's which, but as long as we have it there. See, the shear stresses are in opposite direction. So we're able to get our principal stresses. And this isn't necessary, I guess it was part of the question, but we don't actually need to do that. All we need to do is that for the von Mises is to use this version of the equation right there and make sure that we, actually, we don't have to really do much. We can just pull them right to. But that negative, we have to be aware. There's nothing in there that's will make this negative, so we're okay. So you remember all this? All right. You feel comfortable with it? I was going to go by hand, but it's like right here, and I'm getting tired. Do you want to do any more problems? Or you think you're prepared? I would, as I've been saying since you've known me, work out some problems, right? Just reading them doesn't help much. And you really do want to get like a little faster.
I want to give you more ideas on how to torture it, but if you do a problem like not sample, is there a problem where you could do cyclical pressure loading?
That's an interesting thing to do. I think you basically would use all the same equations, except that, I'm being distracted because I'm thinking about the design one. The design one's kind of more difficult because, they combine the fact that it's round and that you could do MC over I and TR over J both have the, when it's round. So that would get me my brain going to that. But on the other side, if you're doing analysis instead of design, yeah, it wouldn't be too bad because then you would just be sticking it inside of this equation here for right here. And I would put it into axial. I would put the longitudinal into axial. One problem we might have, now that you're asking that, is, this one would actually need to be extended, I think, because you would now have to put in, you can start packing up too. I don't mind. This side is tired. Okay. And equation hunting. What I say not to do, right? Yeah. All right. So you would do extend that equation that we were just looking at in this way for what we just used. I don't know about the stress concentrations. I don't think that would be necessarily something. It'll be a little too torturous right here, but when it came to that combined loading thing, I'm trying to find that same page again. Can't find it. There it is, combined loading. Yeah. So this would get really long because then we would be using that right there. So we would need to use the plus, minus those two times each other, and then this one. Because right now it's basically only looks like that right there, right? Because it has it in one direction, which is the axial. The axial, so the bending, the axial, and the longitudinal from the pressure vessel would all be grouped together. But you would need to do that not only as a square, but also as multiplying by the hoop, and then the hoop by itself. And you make sure you put it in the negative. Yeah, so way to go, man. Now those people next year are so screwed. Yeah. So they'll listen to this video now, and then they're going, man, who said that? We won't tell them. All right, guys, have a good final exam week. I appreciate your attention, and come see my band. No, don't. You might have noticed. You noticed you might have some video issues. Rejoin the session. Reload the session. I wonder if it worked. Well, sorry to anybody if it's missing.
I have a quick question about the shaft project. So, we're obviously supposed to use this big equation for the diameters, like to calculate it.